Hey guys, I wanted to take a little bit of time to look at example 4 out of your notes packet, which I had you do as part of your classwork for today. But I thought I would post this explanation sort of after the fact of you already having tried it, especially since some of you expressed some concerns over how to do it. So here is the basic setup of the problem, right? You got a cloud, all right, so viewed from the side, it's 0.5 kilometers above the ground, and later on in the problem it says viewed from above, it's roughly circular and it's got a radius of 1 kilometer. And I think it's always a good idea when you're setting up capacitor problems to have your list of equations ready to go. So there they all are. All of the equations that we could ever possibly need for capacitors are all right there in front of you. Alright, so let's get going. So if we want to solve part A, we first got to figure out what in the world are they asking for anyway, right? The question was, what's the maximum potential difference in order for there to be lightning and stuff? Well, when we see the term potential, that should probably make us think about V. Potential difference is very technically delta V, but that's a distinction that I'm not really going to get into in this particular course. And the other bit of information we have is the dielectric strength of air. All right, well, if you recall, dielectric strength is the same as the maximum electric field. So given that we are looking for V, and what we're actually being told is the maximum electric field, that should give us a clue as to which equation to use. All right, so pause the video for a moment, look at the equations we've got above, and see which one seems to be the one which will actually help us solve the problem. And here it is, V equals E times D, where the electric field we'll plug in is going to be this 3 times 10 to the 6th number, and D being the plate separation. Well, hold on now, plates, what's going on? Well, all right, a capacitor in general is, or at least in our simple view, has 2 parallel plates on it. If you're not sure what the 2 plates are, we kind of talked about this before, right? But there's one plate, there's the other, and their separation is, I said, 0.5 kilometers. Now, 500 meters is 0.5 kilometers. So if you're thinking, why didn't I just say plug in 0.5? Well, it's because you have to be careful about those units. 0.5 is not okay. That's in kilometers. It's got to be in meters before you plug it in. All right, and so if we do that, everything's good. We get 1.5 times 10 to the 9th volts. Whew! That's a lot of volts. 1.5 billion. All right, now part B wants to know the capacitance of our lightning cloud system. So there's 2 different ways that we could calculate capacitance. I mean, there's several equations that have C in them. So you might be thinking, well, I just solved for V. Why don't I use C equals Q over V? Well, so the problem here is this. If I want C and I only know V, yeah, but I don't know Q. I do not have enough information. There's 2 out of 3 things in that equation that I would need to know in order to solve for the third one, and it's the opposite ratio. I don't know Q or C. So if I only know V, that's not going to help me find C. So I better look at a different equation. And there's our old friend, C equals kappa epsilon naught A over D. Probably you should pause the video and try it yourself, unless you already did try it yourself, in which case you can go ahead and keep playing. But otherwise, pause, see if you can figure out what to plug in there. Alright, I've plugged in most of the things, as you can see. I've got kappa is 1. How did I know? Well, there's only one dielectric constant that I told you guys that I expect you to memorize for the course, and that is that kappa is 1 for air. That's it. That's the only one you need to just know, is that air is 1. And we already knew the plate separation was 500, because that's what we used in part A. But what do we do for the area? I didn't tell you the area of the storm cloud. Well, so there's two equations for circles that people usually remember, 2 pi r and pi r squared. Well, you have to know which one is which. So pi r squared is for the area of a circle. 2 pi r, if you recall, is the circumference, so that would be the wrong one. Now, when we talked about 0.5 kilometers and 500 meters, and if you were confused by that before, don't be fooled again. If you plug in 1 for the radius, you're doing something wrong. Think about that. And there you can see I have 1,000 in there because 1 kilometer is 1,000 meters. All right, so we better get that in the correct units before we put it in. All right, so we've got a value here. Now, I do want to mention something, guys. There's this tool that teachers use all the time called wait time. It's where we stop and let you think about it. And unfortunately, a lot of the time with videos, that's missing. So you have to discipline yourself a little bit, right? If I don't remind you to pause, sometimes you just need to pause me and try and figure it out yourself, right? Not just pause in the event that you feel like you didn't understand something I said, but pause so that you can work past where I've gotten to in the problem. If you feel like you get it, you don't need to listen to me talk and talk and talk. Pause me, work ahead, and then let the video catch up to where you already are, mentally speaking, all right? So feel free to pause if you feel like you know how to do part C. Don't just keep playing. Pause, do it, all right? And then, skip ahead a little bit and see if I've done what you, in fact, did. Now, part C wants to know the energy in the storm cloud. I could also have asked you about the charge on a storm cloud based on our previous work, but for whatever reason, I decided not to ask that question in example 4. I went to energy. So there's a common point of confusion here. People, a lot of the time when I say find the energy, aren't sure which equation to use because they can't remember which letter stands for energy. Okay, so what letter is energy? Yeah, I mean, if I were going to write a children's book, I would make darn sure that I did not use E as for energy because, like a children's alphabet physics book, because it's usually not, right? I would need to say U is for energy maybe, or maybe K is for energy. Yeah, it kind of depends on the energy, right? But potential energy stored on a capacitor, not E. It's never E. All this semester, E is going to be the letter we use for electric field, not for energy. Now, the convenient / tricky thing with energy is we've got 3 different equations for it. It's not necessarily a tricky thing, but sometimes that psychs people out a little bit. They look at the 3 equations and they're like, oh, I have 3 ways to find energy. Do I need to use all of them? No, the reason there's 3 is so that you can pick your favorite. Or perhaps pick the one which is easiest, is most convenient, is based on the stuff you already know. So look back over the problem, the parts we've already solved, and see which one of those 3 equations has the things that you already know. We've got C, we've got V, and as I said earlier, we don't actually know the charge. Don't know the charge. So that should guide you to choose which equation. If you answered 1/2 CV squared, you are correct! Ding, 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 ding! That's right, that's the one to use. We can't use the other 2 without knowing the charge. Now, again, that's not to say that I couldn't find the charge. That would actually be a fairly simple operation, right? I've already got an equation for that. I could calculate the charge based on what I know, but it's an extra step that I would be taking for actually no reason at all. Okay, so we plug in our values and we get 6.26 times 10 to the 10th joules. Now, I thought it might be good for you to get some kind of a sense of how large that number is. Because sometimes, you get a value in physics and you're like, oh, great, okay, and then you move on to the next problem without really stopping to think about what that number means. Like, what is it telling me about this scenario? So I went on Wikipedia and looked up orders of magnitude in energy, which is one of my favorite Wikipedia pages. It's kind of a weird thing to have my favorite be, but whatever. That page gives a lot of different scales, and it says that 1 ton of TNT is about 4.2 times, so what? So this is like, I don't know, a solid 12 times the number of joules of energy as a ton of TNT. One lightning strike, 12 times the energy of a ton of TNT. Does that seem reasonable? I don't know, maybe. Well, it turns out that same page also says that the average lightning strike is only 1 times 10 to the 9th joules of energy, which is still mind-boggling, right? That's still an actually enormous amount of energy, which is why a lightning strike will absolutely shatter a tree. But typically a lightning strike doesn't do the same amount of destruction as a ton of TNT. Okay, so it's actually on average only about a fourth of the energy of a ton of TNT. So maybe something was wrong about my setup in the problem. All right, that's entirely possible. Or maybe there's some other assumption that we're making that's incorrect. But still, that's really not that far off. We're only off by roughly a factor of 10. So yeah, lightning strikes contain an enormous amount of energy.